we come back to this slide and we are near completion of the subtopic of manufacturing of powder. So, we were looking at gas atomization, and over here we would take a look at the empirical relation, but before that let us take a look at this plot. Here what you see is the particle size, and on the y axis you have cumulative percent. So, if the plot is more to the left, it would mean it has a smaller particle size, and if it is much steeper, then it would mean it is very narrow in distribution. What we see is that slopes do not change much. So, the overall size distribution remains same no matter what is the pressure that is being applied or what is the melting temperature or what is the melt temperature. So, if you change the melt temperature, it is not going to affect the overall slope. However, if we look on the shift of the plot, then we see that pressure and the melt temperature, both of them have effect on the distributions or the overall average distribution. So, when you let us look at these two, where we are applying the melt temperature is 720 degrees Celsius. So, we have kept one parameter constant and we apply higher pressure. So, here the gas pressure was 6.2 megapascal and over here the gas pressure is 8.7 megapascal. We see a left shift of the distribution, and that means that the powder size have become smaller. And at the same time we also see that there is some effect of melt temperature. For example, if you compare this one and this one, over here the temperature is the pressure, gas pressure is kept constant, which is 8.4 megapascal, but the melt temperature has been increased. So, if you increase the melt temperature again, you are able to see a drop in the particulate size. So, these are some of the experimental results, and based on these empirical relations have been obtained to decide what would be the size of the particle. So, let me write down that empirical relation for the sake of completion. So, d is the particle size, and we will explain the other parameters very soon. And there is also, to take into account turbulence, a quantity called Weber number is also utilized. We will show what is the relation for that Weber number. We will explain the other terms, but this is the Weber number that we were talking about, and this is given by the relation so this is subscript m. So, this is the Weber number which takes care or which takes into account the turbulence, and now let us look at what the various quantities mean. K is just is nothing but some empirical constant. So, you have these relations, and proportionality constant for this to diameter is given by this K. So, this is the empirical constant. D is equal to melt stream dia, and what you see is that the particulate size is directly proportional to D. So, if you this you can also have expected from the relation that we showed for ligament size to sphere size. So, over there also we saw that if you want to decrease the diameter of the particle size, you have to reduce the ligament size, and the ligament size is again proportional to this D, which is the stream diameter. Mm is the mass flow rate of melt stream. Mg is the mass flow rate of gas. Eta are nothing but the viscosity. So, eta m is the melt viscosity, that is the liquid melt. Eta g is the gas viscosity, and V that we see over here is the velocity, gas velocity of the gas. and gamma m is the melt surface energy. And lastly we have this dl, it is the melt ligament diameter. So although over here we see diameter is proportional to the small d, which is the melt stream diameter, but Weber number is also proportional to this ligament diameter, which comes in denominator. However, you would when you put in the values, you would see this would be the more dominant term. This one is, or you can say this ligament diameter is affecting the turbulence. So the turbulence factor is being taken into account by Weber number, which is also indirectly contributing to the particle diameter. So this is the relation for the empirical relation which defines the particle size for gas atomization technique. And like I said, I will spend just a little bit of time on liquid and water atomization. So most of the time the liquid that is used in this kind of atomization technique, it is water. Over here we will just, as you can see over here also the melt is coming down just like in the previous case, and through a jet you are forcing or you are causing the water to splash against the melt, and this again causes disintegration of the liquid melt. So the liquid that is coming through the jet with the high energy is disintegrating the liquid melt that is coming through over here. So the overall principle, as you can see, is still the same. However, there are some other parameters that start to affect, and the empirical relation that we get is a little bit different from what we have seen over there. Over here the angle at which the water spray is splashing the melt, so this angle theta also comes into being. So let us say this is alpha, because that is what we will use in our relation. So this is an angle alpha. Then there is the P, the constant which incorporates both material and atomization technique, and we will see about that in couple of minutes. And there is also the V, which is the velocity. So these are the parameter that will affect the water atomization technique and the particulate size that comes out of it. Another very important aspect or parameter which differentiates liquid atomization from gas atomization is the very high cooling rate that you will get in over here. So the cooling rate here would be very high. So now what do you think would make how will it make a difference to the overall particle size or particle shape? You remember over there we had particle shape going from flake to ligament to ellipsoid to finally the spherical shape. Now since the cooling rate is very high, what will happen is that probably the particulate or the particles that are coming out will freeze even before they reach the equilibrium spherical shape, and that would mean that what you would get out of it will be somewhat random shape. And now if you look at the particles that you get over here, they are indeed not as spherical as you were getting in gas atomization technique. So this is because you are getting very high cooling rate. So the quench rate or the very high cooling rate is what is causing somewhat irregular shape. This is as round as it gets for liquid atomization. So important process variable for the liquid atomization, as you would see when we write down the equation, are water pressure and water velocity. Higher water pressure leads to higher water velocity and smaller particle size. So now that we have talked about this in a little bit of detail, so let us look at the empirical relation which will define the particle diameter with respect to the several parameters that affect it. So again D will be the particle diameter that you obtain using liquid atomization technique, and this will be given by beta ln P and V sin alpha. You remember alpha was the angle between the water jet and the melt. Beta is again some constant. This incorporates or this takes into account all the material and atomization technique parameters. So, it incorporates material parameters and other atomization parameter. P is, we know, water pressure. V is water velocity. And alpha is the, so here what you would see is that the relation looks somewhat similar, but that is because these are the more important parameters. Other not so influential parameters are clubbed into this beta. This is the empirical relation for liquid atomization, and the previous one that we looked at was the empirical relation for gas atomization technique. So, now we come to the last slide on atomization technique. So, this is a technique that I was talking about earlier, so that you can use atomization also for creating nanopowders, and over here there will be a little bit of difference. One of the biggest difference is that this will be a very high vacuum chamber, because you do not want the particulates to clash or strike against any other gas molecules, because that may also cause condensation and even heterogeneous condensation. And over here this is the liquid nitrogen. So, you want a very super cooled condition, so that you get very homogeneous nucleation. So, this is a liquid nitrogen column, and this is the evaporation source. Over here you are heating whatever material you want to create, and these molecules, or these are in you can say almost molecular state, and when they reach this liquid nitrogen, which is very low temperature, then over there they, because of the super undercooling, very large undercooling, they will undergo homogeneous nucleation. So, what you want is the over here the vapors to come into contact and then very quickly solidify because of very large undercooling and under homogeneous nucleation condition, and that is when you will get very fine powders. So, these fine powders come over here, and there is a scraper which will come down, and all the powder particles will get collected over here. So, this is a schematic which tells you how you can get even nano size scale powders using atomization technique. And if when you are talking about this, then this will also involve science of nucleation, solidification and powder metallurgy. So, this is a much more involved process, so to say. To end this subtopic on the formation or the powder manufacturing technique, will look at one example problem. So, let us say we have 100 grams of iron oxide. So, we are looking at the example related to oxide reduction. So, let us say we have 100 gram of iron oxide that is reacted with 1000 centimeter cube of pure hydrogen. So, this hydrogen that is being reacted is given in volume because it is in gaseous state, and the iron oxide that is being reacted is given in weight because it is in solid state in a closed system at 1 atmosphere. So, you are given the pressure using a temperature of 400 degrees Celsius for extended time. What is the weight of pure Fe that would be formed? So, given this information, you have to find out what is the weight of pure Fe that would be formed. So, what we will need to do is look at this equation. You see, this is the equation that takes place, or this is the reaction that takes place. So, FeO in solid state reacts with hydrogen in the gaseous state to form iron in the solid state and gives out moisture in the gaseous state. And the temperature, pressure, phase diagram for the different phases are given over here. This is the region over which iron is stable, and this is the region over which Fe3O4 is stable, and if you go to even higher temperature, FeO becomes stable. So, but overall this is your line of equilibrium. Now, here what we will need to do is first find out what is the number of moles of hydrogen and number of moles of H2O that will be formed. And if we know what is the number of moles of hydrogen that has that exists and compare it with what you was earlier, which is based on the F 1000 centimeter cube, we will know how many of them have reacted. So, how many moles have reacted, those many moles of FeO would have reacted, or that many moles of Fe would have formed. So, that is the overall thought process that we are following. So, what we will do is, we know from 1000 centimeter cube of pure hydrogen, and it is already given STP, we will calculate the number of moles, total number of moles, and it comes out to 0.0446 moles. And then next we will look at what is the ratio of H2O and H2 molecules. That we will be able to know, because we know what is the pressure ratio of H2 and H2, PH2O by PH2. So, here is your 400, this is the temperature and this is the pressure that we are looking at, sorry, this is the temperature, and at this temperature we will look at the equilibrium diagram where both Fe and Fe oxide exist together, and we will assume that we are still in the, both of these are FeO. We are not going to complicate by assuming that this is Fe3O4. As you can see, we are starting with FeO. So, we will assume that this is still FeO. So, we are at this reaction boundary, and the pressure ratio that we see over here is 0.1. If the pressure ratio, the partial pressure of H2O to the partial pressure of H2 is known, which is equal to 0.1, then this has to be proportional to the number of molecules of H2O to number of molecules of H2, and therefore, we now know the number of ratio of number of molecules of H2O to number of molecules of H2, and which is equal to 0.1. But we also know the total number of molecules of H2 and H2, because we started with 0.0446 moles of overall hydrogen. So, if some of them have reacted, each mole of H2 that reacts, it will form 1 mole of H2O. So, the number of moles are not lost. For each mole of H2, there will be 1 mole of H2O. Therefore, whatever is this 0.0446, that will also represent the total number of moles of hydrogen and moisture. So, NH2O plus NH2 is equal to X, which is equal to 0.0446. So, if you take these two relations, that is NH2O plus NH2 equal to 0.0446 and NH2O by NH2 equal to 0.1, you can calculate that number of molecules of H2O is equal to 0.0041. Now, this is the number of molecules that have reacted. So, what you need to know, or what you, so we have already obtained how many molecules have reacted. So, those many molecules of iron must have formed. So, we will multiply this by the weight, molecular weight of iron, which is 56. So, 56 times this NH2O, which is 0.0041, and therefore 0.2296 gram of iron should be formed. So, we started with 100 grams of iron oxide, and if we maintain these conditions, then we see that 0.2296 gram of Fe is only formed. So, this is a very small number, and how do we increase it? We discussed it when we were talking about oxide reduction. We can very easily increase this by taking away the H2O molecules. So, now it is not, we are not saying it is a closed system, this system is open. We will continuously take away H2O molecules. If H2O molecules is taken away, more H2O will react and it will lead to further 0.2296 gram of Fe2 form. Then again we take away, I am saying this in steps, but in reality it will be taking place in continuous manner. So, again we take away that H2O molecules and 0.2296 gram of another 0.2296 gram of Fe will be formed, and so on. The process will keep continuing until all of FeO has been converted to Fe. So, this is the example problem on oxide reduction method of manufacturing powder. And now next we will move on to our next topic. As you remember, we have now covered introduction to powder processing. We looked at various important powder characterization parameters and techniques. Then we looked at so many different ways to manufacture powder, and now we come to consolidation, powder consolidation. So, let us say you have powder and you put them together. Now, you want to know, if I just put the powder together even before compaction, what is the relative density that I should get? What are the number of point contacts between each of the particles? Because it is at those particular points where the powder particles get in contact, where the eventual centering will start. So, these are some of the questions that we will be able to answer when we look at powder consolidation. So, the first thing that we will look at in terms of powder consolidation is particle packing. So, there are several ways, we already are aware of some of those about particle packing. From our crystal structure knowledge, we know about FCC, BCC, etc. So, we can also take them as a model of how the powder particles have been fitted and find out what should be the packing fraction, which will be equal to the relative density. So, let us look at some of the well known packing and the relative density that you would get over there. So, let us take for example, to begin with we will keep it simple. So, we will take mono size spherical particles. Okay, so, this is a hypothetical scenario, because in reality you will never have mono size, but this is just to give us an idea how to relate some of the important parameters to each other. And when we say packing fraction, this will be equal to relative density which will vary between 0 to 1. And we also know that packing fraction is proportional to coordination number, that is number of nearest neighbor. So, with this let us start with some of the simple structure. So, we will look at some regular structure. And we will look at what is their packing fraction and what is their coordination number. So, let us first look at simple cubic. Okay, we are not remember we are not talking about crystal system. We are using the term similar to what is used in crystal structure, but we have at the corners or wherever their atom used to sit, we will be having only powder particles or spherical, and that too mono size spherical particles. So, this is a regular simple crystal BCC, simple cubic. This is simple cubic. So, your atoms are sitting only on the corners, and you would know what is the packing fraction for this. The packing fraction for this kind of system is 0.52, coordination number is 6. Let us get to a different system, body centered. Again we are not talking about crystal systems. At the edges or wherever the atoms should have set, we have powder particles. But the packing fraction that we obtained for crystal system is also valid for this, as far as we have a monospherical single particles, monospherical spherical particles. So, at the, other than the corner, you also have at the body center, and for this we know that packing fraction or the relative density is 0.68 and coordination number is 8. And then we also have face center. Putting them at one place makes it easier to compare and comprehend. So, other than the corners, you also have atoms at the faces, at the center of the faces, and then also on the other back faces. We are not drawing the back faces, and with the face center is supposed to have the best. Okay, if this is not coming in the same line, let me put them together in same line. So, this is the highest packing fraction that you see for any system, and it is 7.4, highest. and what is the coordination number, that is also highest, which is equal to 12. So, these are the some of the most well known systems. We are borrowing our understanding from atomic system or a crystal system, and we are using it over here, and now we will relate it to some, and we will relate now some of the other parameters that we know from, again from our understanding of crystal systems. So, we know that number of particles Np is equal to number of particles per unit bulk volume. So, what we need is packing fraction divided by the volume. So, this is saying that there is 0.74 of the cube is filled. So, what we are saying here is 0.74 divided by the total volume of each particle is the number of particles per unit bulk volume. And another parameter that we will define is number of particle contacts. And these are all our understanding borrowed from crystallography. So, this is given, let us say, by NC. You can write it by coordination number by 2 times Np. So, number of particles per unit volume, and each of them have coordination number, some coordination number. So, that is the total number of coordination number, but it will be shared by another particle. So, we will count only half that coordination number. So, this gives you the number of contacts per unit volume. And for if we take Np equal to 6 by pi d cube times Pf, then this becomes 3 into Pf, and you would see that we are using these terms Pf, P and Cn, because then we will be able to generalize it even for the condition where crystallography does not apply, for a non-regular structure. So, now we have written in a more general term the relation of number for the number of particles per unit bulk volume, number of particle contact per unit volume, and this is how it will look like. And this these are very straightforward when we are looking at regular structures, which again, like we said, for the systems that we borrowed from crystallography. But then I have also said that we do not always get a regular system. In fact, these are ideal case scenarios. In real life, what you will get is not really a simple cubic or a body centered or a face centered. What you will get are more like what is called as loose random packing. So, let me say this is non-regular. Those were regular structures, they had long range orders, but in general what you will get is not something which has long range order. So, this will be either loose random packing or dense random packing. So, in this case, if you take Pf, it will come out to approximately 0.6. If you take the packing fraction, in this case, it will come out to approximately 0.64. And these are approximate numbers based on our experiments of different kinds of powder. So, and these are the two most observed ones. So, you will see loose random packing, that is when you have just put in the powder and not tapped it. Dense random packing, when you have put in the powder in a jar or a cylinder and then you tap it. You must have seen that when you tap, for example, you take grains, you put it in a vessel and then you tap it, then the overall volume that was occupied reduces. So this will be related to tap, also what you can call tap density. So after tapping, how much you are getting, and this is before tapping. So we'll get back to this and we'll continue our understanding on powder consolidation in the next lecture. So we'll end over here and meet and see you next time. Thanks.